In this video, we are going to continue to talk about the different nucleophiles that interact with aldehydes and ketones. At this time, we're going to focus specifically on the nitrogen nucleophiles. Under acidic conditions, aldehydes and ketones are going to react with a primary amine to form a particular functional group that you may not be familiar with that is called an imine. When we look at the highlighted green boxes, we can notice what an imine is composed of. An imine is going to contain a carbon-nitrogen double bond. And in essence, as you can see, is that the oxygen atom is going to be lost, and we're going to see in the mechanism how that occurs. And in its place, we're going to have the nitrogen atom and the alkyl group that is bonded to it in the place of the oxygen in the functional group that is formed. Again, this reaction specifically requires acidic conditions. When we look at the mechanism for the reaction, we can notice that the steps may be a little bit different what we assume or what we have observed previously with other reactions that are going to be under acidic conditions. In the case of a primary amine interacting with an aldehyde and ketone, understand that the first step of the reaction is going to be the amine attacking the carbonyl group directly. In turns, the electrons go up to the oxygen atom, and as you can see, we're going to form an intermediate that contains a nitrogen that is positively charged and an oxygen that is negatively charged. In the next step of the reaction, we are going to have that intermediate going to get protonated at the oxygen atom, and our oxygen atom is going to now become neutral. Then on the third step of the reaction, we're going to have a deprotonation of the nitrogen that was incorporated in that first step, and that's going to give rise to an intermediate that is called a carbinolamine. Now, once we have that carbinolamine, because remember, overall, we are trying to remove the oxygen that was first part of the carbonyl, we are going to protonate that oxygen. When the protonation of that oxygen occurs one more time, now we're making it a great leaving group. So, in the next step of the reaction, what we're going to have is going to be the nitrogen going to have an intramolecular flow of electrons in which the lone pair of the nitrogen is going to come down and the oxygen is going to leave as water. And that's where we form the carbon-nitrogen double bond. And in the last step of the reaction, we're going to have the deprotonation of the nitrogen that results in the formation of the imine. Even though this reaction it is under acidic conditions, the protonation of the carbonyl is not the first step for the mechanism of the imine. Let's take into account that remember that amines are bases. They are weak bases nevertheless, but they're still bases. So in the process of acids, as you can see, if we have HCl as an acid, because of the low pKa and the ability of the amines to act as bases, one of the things that we're going to see, and it's one of the fastest reaction, is going to be the acid-base reaction between the amine and the acid, which is going to be resulting in the formation of an ammonium ion and a chloride ion. So in essence, what we are forming is an ammonium salt. Okay, so the ammonium ion is the acid catalyst present in the reaction. Now, let's note that ammonium ions or ammonium salt is not acidic enough to protonate an aldehyde or a ketone, but it is acidic enough to transfer protons to the negatively charged oxygen in the second step of the reaction. So if we observe the reaction one more time, understand that at this point in our mechanism, our ammonium salt, specifically the ammonium ion, is the one that is going to be acting as a general acid in order to protonate that oxygen that is formed after the first step of the reaction, which was the attack of the amine to the carbon and the carbonyl, generating that negative oxygen. So it is important to note that that is the involvement of the ammonium ion in the reaction. Understand that since that acid is going to be present, every time we see HA, we can assume that that ammonium ion is going to be our source of protons. Now, we already established that the formation of an imine is going to require a primary amine. And a primary amine is going to be a nitrogen atom that contains one alkyl group. It could be aryl too. Now, understand that what happens if we have a secondary amine. And a secondary amine, as you can see, is going to be a nitrogen atom that now is composed or is surrounded by two alkyl groups. Now, understand that the reaction, okay, is going to require acidic conditions, okay, and the mechanism is pretty much very similar to the imine formation, except that in the last step of the mechanism, instead of deprotonating at the nitrogen atom, because there's no proton specifically present on the nitrogen, because as you can see in that last step, we're going to have two R groups on the nitrogen. What occurs in that system is that then we are going to have deprotonation of the carbon atom next to the carbon that was part of the original aldehyde or ketone. So as you can see, the deprotonation is going to happen at this position, and the result of reacting an aldehyde or ketone with a secondary amine is going to be the formation of this functional group that is called an enamine. Now, understand that there are reactions that have specific need for some of these nitrogen nucleophiles. And now I would like to introduce the Wolff-Kishner reaction reduction. So, In the Wolff-Kishner reduction, understand that this is a two-step synthesis that is going to convert specifically a ketone to an alkane. So during this reaction, we are going to completely remove the carbon-oxygen double bond, and in our product, as you can see, we're going to be incorporating two hydrogens to the system. So this is again going to remove the carbonyl functionality by not having in the product the double bond oxygen. Understand that the first step of the reaction is an imine formation between the ketone and specifically the reagent that is called hydrazine, okay? Which in essence, hydrazine is just like a primary amine. Now, in the second step of the reaction, it's like an elimination that is going to be occurring in order for that potassium hydroxide, water, and heat to generate and incorporate those two hydrogens to our molecule. Understand that we're going to generate nitrogen gas in the system as part of the product. But again, nitrogen gas is an inorganic product. We don't need to incorporate it into the product of the reaction. We are going to be focusing on the organic product. So, because the first part of the mechanism, meaning the ketone interacting with the hydrazine, looks like the imine, we don't have the steps for it. Let's now focus on the second part of the reaction, which is once we have that imine-like structure, what happens when we have the potassium hydroxide and the formation of, or of the, I should say, the elimination of the nitrogen in order to incorporate the two hydrogens for the reaction. And this is how the mechanism proceeds. In the first step of the reaction, one of the protons in our imine-like structure is going to be removed, okay? And as you can see, that is going to be forming a resonance stabilized intermediate. Then that intermediate is going to be protonated, specifically at the carbon anion that we have in the molecule. Then another proton transfer occurs is specifically by deprotonation of the nitrogen that we have had incorporated in the system. Once that happens, then understand that overall we can have that nitrogen gas forming, okay? Because we are going to have the nitrogen lone pair go and form that N2 group, and the electrons are going to move back to the carbon, and this carbon anion, as you can see, it is formed right here. And then in the last step of the reaction, that carbon anion is going to be protonated, and that's how we generate the product. Let me renumber this. This is step 3. This is step 4. This is step 5. Now we're going to proceed to talk about hydrolysis, which is something that we observed previously earlier in this video series. One of the things that we learned earlier in the chapter was that acetals are incorporated with acids. And as we saw in a previous example, acetals are actually hydrolyzed under aqueous acids to generate a ketone or an aldehyde, depending on what you started with, okay? And two equivalents of the alcohol. When this happens, it is simply the reversal of the acetal formation. So if we have an acetal and we put it under acidic conditions, um, depending, okay, this one we know it is based on a ketone because as you can see there's 2CH3 here, so that's why we have a ketone. Now, understand that acetals only react with water under acidic conditions. So what that means is that acetals are base stable. So if you add a base and water to it, there will be no reaction. So for example, when you are incorporating acetals as protecting groups, as we saw earlier in the chapter, to remove the acetal as a protecting group, you may not suggest the use of base and water. It must be acid and water in order to remove them. Now, let's go over the mechanism of how the hydrolysis of the acetals actually occur. So, starting from the acetal, again, we are going to be removing this group via acidic conditions. The first step of the reaction is that the carbonyl group is protonating, and that is going to specifically, as you can see, create a more electrophilic system. Now, then in the next step of the reaction, the oxygen that was not protonated is going to do an intramolecular reaction, and we're going to have an alcohol being removed from the system and leaving as a leaving group. Now that we have this electrophilic species, okay, then the water molecule can go and attack the carbon in the carbon oxygen double bond, putting the electrons up to the oxygen. So we're going to have water function as a nucleophile and attack that activated electrophile. In the next step of the reaction, as you can see, water is going to then deprotonate the water that just was incorporated in the previous step, okay? And that's going to give us a hemiacetal. Because we need to remove the other OR group in the next step of the reaction, that hemiacetal gets protonated specifically at the OR group, okay? Make sure that you follow the arrows to have the correct flow of electrons. So once the protonation happens, utilizing hydronium, the hydrogen-oxygen bond is going to break. Then we're going to have another instance in which we're going to have an intramolecular reaction. And in this case, we are going to then remove the other alcohol equivalents, resulting in a protonated ketone. And again, in this case, we have a ketone just because of the general structure that we started with. And in the last step of the reaction, our water molecule is going to remove the proton and the ketone to just generate the ketone at the end of the day. Now, understand that the molecules that we introduced a few moments ago, imines and enamines, also undergo hydrolysis. Hydrolysis of imines and enamines, understand that those reactions are going to be very similar mechanisms under acidic conditions. Okay, so imines and enamines, as you can see, if you put them on acid and water, are going to regenerate those ketones that we started with. The mechanism for the hydrolysis of imines and enamines is simply the reverse of the mechanism for the formation. So make sure that you practice the mechanism on your own to illustrate the regeneration of the ketone under these conditions.